how do you think the business will be? It's curious actually. Okay, so orbit of velocity is what? 8,000 meters per second. So I gave you the general formula. So remember that the general formula of 40 of determining the orbital velocity, determining orbital velocity of the satellite involves the S at or in any orbit is given as this. Mean that the square root of the universal gravitational constant, mass of the S, over radius of the S plus the height h. Or I derived it for you that given such radius of the S, square root, acceleration gravity, radius of the S plus the height, just like this. Right? So there it is in your mind. So these are the general two forms of general formula determining what orbital velocity of 40 of the satellite. So orbital velocity close to the Earth's surface. We say that the satellite is on the Earth's surface close to that one. Okay, fine. So I would like to teach you again, just like the second from the last concept of this lecture of planetary and planetary motion and satellite motion. I would like to teach you about the period. Say the period. Then the concept of period in pendulum, simple pendulum. The period of the satellite. First of all, what does it mean? Period of 40 of the satellite. So that's the concept that you have to cover before we got the last we say call it not last, it's the last concept for this lecture 5. So the question is, what does it mean? What does it mean by the period of the satellite? And the question that you have. So he said that the period of the satellite is the time, can be asked to define in section A, is the time taken by the satellite to complete one revolution. Complete one revolution around the Earth's surface. So that's the meanings of 40, or the meanings of the word period. is the time taken by the satellite to complete one revolution. Complete one revolution around the Earth's surface. Complete one revolutions around the Earth's surface. So that's the definitions of 40. That's the definition of this time period, of the term known as period, right? So remember that this is mathematical physics. So we are very interested in derivation. So doing derivations, solving problems, that's the chorus of physics. Okay? So enjoy this chorus. And they were teaching you to think differently, like how the physicists and even the engineers used to think. So derivation. Derivation of the period, right? Period. Derivation of the formula, not the period. Derivation of the formula. The formula that determines the period of the satellite. Period of the satellite. Revolving what? The S. Orbiting the S. So we'll be following some steps. The first step, we say that we call the formula of 40 of velocity. We used to say that velocity is equal to distance over time, right? Distance over time. That is true. If we make time the subject, then we come up with this. So if you make time the subject, then the formula will become like distance of velocity of velocity. Right? So this time now, because the satellite will be revolving around the S several times. So when it completes one revolution, then it is going to revolve the S in the same orbit second times for the second revolution, for the third revolution, for the fourth revolution, for the fifth revolution, for the sixth revolution. So it means that that repetitions of the time, because it's going to spend the same time, okay, to revolve, to complete one revolution, then that's what you call the period. So period is a time taken by the satellite to complete one revolutions around what the Earth. That's the definitions of the period. So this period now, which is in physics and also in science, take by capital T, it will be distance traveled, okay, or distance covered over velocity. So this is general. So in case of the satellite now, we say that in case of the satellite is orbiting the Earth in the particular orbit. So suppose that this is the orbit of the satellite, this is the Earth's surface as I drew it. This is the center of the Earth. Here we have mass of the Earth. Here we have radius of the Earth. Here we have height where we place the satellite. And then here we have mass of the satellite. If you do remember, we have centripetal force, we have force of attractions, we have weight of delta of the satellite. So what I want to tell you, it means that the satellite revolving, right? Revolving the Earth in this orbit. So when it's revolving the Earth in this orbit, what's going to happen? So this is the mass of the satellite. So it means the satellite is revolving the S, okay, in its particular orbit. So when it's revolving the S in particular orbit, so the velocity that the initial velocity or the velocity that is revolving with, we say that it is orbital velocity. So it's revolving its orbit by the orbital velocity. So this velocity is orbital velocity. And then the distance now is not the linear distance. The distance is a cycle. So this is the cycle. So now in case that if you want to know the distance of the cycle in mathematics, we used to call this phenomena as what? Circumference. Right? Circumference. In Swahili, the circumference, we call it mzingo wa duara. Circumference of the cycle. Right? Because, you know, if just I let you know in Swahili, I connect you from what you've been known and what we are trying to teach you. So the distance means that we say for the satellite, right? For the satellite, we say that the distance is equal to what? The distance is equal to circumference. Circumference of what? Circumference of the orbit. Circumference of the orbit. Then the velocity is equal to the orbital velocity, which I told you. I told you previously in this lecture. So if that's the case, now we say the period of the satellite, TS, period of the satellite, it will be the circumference of what? Of the orbit of the satellite over orbital what? Orbital velocity. So this is the formula. And that is the second step. So this is the second step. Okay? The third step, we say that the circumference now, circumference orbit, for this case, we usually used to say that that is 2, or that is equal to pi times what? Diameter. Right? But for this case, you say that the circumference, in case that we know the radius, we say that this is 2 pi r. 2 pi r, diameter is equal to twice r radius of the cycle. So then, if that's the case, you say that the circumference now, if you consider this figure, circumference, consider this figure, is equal to twice pi times what? Radius of the S plus the height. If now we take considerations of this figure, this is the radius of the S from the center of the S to the surface of the S, and also from the S's surface to the orbit, to the satellite orbit, we call it H. So that's the circumference. And then we say that orbital velocity, I have already told you, we have two forms of the formula. Orbital velocity is equal to the square root of gravitational constant, mass of the S, then radius of the S, plus the height. Or the other one. Or the other ones, we say that this is equal to what? Radius of the S, acceleration gravity, then we say what? Here we have radius of the S, plus the height. Okay? So if that's the case that we say that the period of the satellite is equal to the circumference, which is equal to 2 pi, radius of the S plus the height, and then divided by the square root of what? Universal gravitational constant, mass of the S, divided by radius of the S plus the height, where the orbit of the planet, no, the orbit of the satellite is from the S's surface. Okay? So now we have to simplify. at the force system. Do you enjoy the beauty of gravitation? I believe that you enjoy. For me, I enjoy the beauty. Gravitation is very beautiful, physics is very beautiful, mechanics is very beautiful, and even yourself who is watching this video, you are very handsome boy, or you are very beautiful girl. Okay. Yeah, because you are an image of God. So because you are an image of God, God is always handsome. And He's creating beautiful things. So that's why that you are beautiful. It's not a joke. It's not something that maybe I want to make so radius of the S plus 40 plus the height. And then we divide, so this one. So we go up. I think that I forgot to write the step first thing. The first system. Let us simplify that formula and see what will happen. So we say that the period of the satellite is equal to the circumference, which is 2 pi. And then we have what? Radius of the S plus the height. We divide by the square root of what? So we divide by this one, square root of universal gravitational constant, mass of the S, over square root of what? Radius of the S plus the height. So this one is over 1. So because you are dividing fractions, then the denominator becomes the numerator, and the numerator becomes the denominator. So we say that the period of the satellite is equal to twice pi. Then you have radius of the S plus 40 plus the height. And then we say that divided by 1, we multiply by the square root of what? Radius of the S plus the height divided by the square root of gravitational constant, mass of the S. Right? And then we say that the period of the satellite, this will be equal to what? Twice pi. So then if I want now to plug this value into the square root, then we are going to have radius of the S plus the height square. The height square, we multiply by the radius of the S plus the height power 1. So then we divide by gravitational constant, mass of the S. So now the period of the satellite, right, it will be given as 2 pi, right? And then we have the square root of what? The square root of radius of the S plus the height where we place the planet, then divided by gravitational constant, mass of the S. So then this is the formula that we need to do miracles. Period, to calculate the periods of 40 of the satellite. Right? You enjoy. Okay, that's one of the form of the formula. Right? Good. So in case that we want to replace the formula with what we had in advance, we say that that will be the fifth step. The fifth step, we say that we have to recall. I told you, I gave the NB not before, that the products of universal gravitational constant times mass of the S is equal to acceleration due to the gravity times radius of the S square. I think you remember that. So we can substitute it there. So you say that the period of the satellite also, we can express it is equal to twice pi. Then we say that the square root of what? Radius of the S plus the height cubic. And then this one we divide by acceleration gravity, radius of the S square. So if we simplify, period of the satellite is equal to 2 pi radius of the S, then this is the square root of what? Radius of the S plus the height. And this one is cubic divided by acceleration due to the gravity. So this is the constant. Okay? So this is the truth, the story, 40 of period of the satellite. Then, what do you think you got that formula as a physicist student? What do you think? the thought that might come in your mind, it is in case that we can determine the periods of the satellite to complete one revolution when its orbit is near or is near to the Earth's surface in such a way that the height of from the Earth's surface to the orbit is negligible. So that's what we can do. So the 60th step, let us just say that the 60th step, we say that if the orbit of the satellite, is closer to the Earth's surface, in such a way that the height from the Earth's surface to the satellite, to the orbit, is very, very small. So, if that the case, means the sum radius of the Earth plus the height, this is closely or is estimated into the radius of the Earth. So if that the case, now we take considerations of this form of the formula, we say that now the period of the satellite is equal to twice pi of what? Over radius of the Earth, right? Radius of the Earth. And then in numerator we have now radius of the Earth plus 0, which is height 0. This means that the height is 0, okay? But Q divided by what? Acceleration gravity. So then, if that the case, we get twice pi, and then in the numerator, here we get radius of the S cube, G radius of the S square. So we simplify, and then we say that period of the satellite, this is equal to period of the satellite is equal to twice pi, and then we say that under root of 40 radius of the S of acceleration gravity. This is equal to twice pi, radius of the S, 6.4 exponent 6 over 9.8. So then the period of the S, the period of the satellites revolving the S, if you use your scientific calculator properly, we'll get it is 5,077.54 seconds. So it is 5,077.58 seconds. Very minimum times, means that this will be a high speed satellite. So then if you convert that period into minutes, this is equal to, when you say that into minutes, means that if we divide, if you want to convert into minutes, the satellite will complete one revolution in 84 minutes. Just 1 hour and 23 minutes. Fantastic. In an hour, you complete to revolve the Earth's surface. This is amazing satellite. Okay? So the period of the satellites, let's say it is 50 or 5,077.58 seconds. And then so divide by the 60 seconds to get minutes. So the period of the satellite is equal to 84 minutes. So a satellite will take only 84 minutes just to revolve to complete, not 84.6 minutes. 84.6 minutes. But this now, 84.6 minutes, depends on the reference book. For example, when I checked your reference book that's called the Nelcon, the period was estimated at 83 minutes. So in Nelcon, this period of the satellite is estimated to be 83 minutes. right? Again, I have referred the book called the Roger Mancaster. This video also is estimated to be 80 what? In Roger 85, in Chad 1 84. This is 85 minutes. You have to go through all of these books, my dear student. In Chandi 2, in Chandi 1, we say that this period is approximately equal to 84 minutes. Right? So that's the period of the satellite revolving near to the Earth's surface. So now it is time for the homework. Time for what? For the homework. It's time now for you to try the questions. I've been solving, I've been thinking how can I teach you? So now this is the time for my beloved students who is watching this video to teach me advanced physics and especially gravitation. Are you ready? Yes, let us go to the business. So now it is time for the homework. Tell your neighbor if you're watching group, homework. And this is homework 5. I have 2 interesting questions. Don't worry. The first question, question 1, this homework, derive the formula of determining the period of the satellite as a function of density of the S, density of the S, density of the S, radius of the S, radius of the S, radius of the S, RIH means radius of the S, gravitational constant of the S, universal gravitational constant, and the height of the planet. That's the first question. Derive that formula. It's a unique formula, interesting formula. It will help you to solve many problems and will be testing your concept of derivations. Don't claim these formulas, just know where you have to start and what are the steps that you have to follow along. The second question is this: derive the formula, okay, that determines the height of the orbit, of the satellite from what? From the Earth's surface. That's the question. So these are, like to call them, these are the 2 simplistic questions than ever in gravitational mechanics. So make sure that you try your level best to derive those formulas, and then think, first of all, before you derive these formulas, it's better to go through, to review the session 5 or lecture 5 or period 5, so to understand the whole concept of derivation that I've been teaching you from the beginnings of the lecture to the ends, or from the middle of the lecture to the ends of this lecture, and then try to derive yourself. Try. And when you are deriving, don't just derive because you're deriving for me. Derive for yourself. I know how to derive these formulas, but I want you to try yourself. In case that you have any troubles, you fail to understand how to do this homework, I will be there in the comment sections to help you where you have got, you didn't get well and didn't understand, and where maybe you get, you failed to proceed. Don't worry that we are together in this business. I know that it's a little bit a tough business, but I have to mentor you, and I have to make sure that you own these materials, and even you do the best more than what I used to do, I who is teaching you this material. Thank you very much. I thank God who has given me this ability to teach you all of this stuff, and even to remember them, find different teaching ways, gathering the materials, readings, collecting, teaching. So I thank God for that, and I thank you also for your time that you have taken to watch this material. I believe that you enjoyed. Make sure that you subscribe onto this channel, that Tanzania Online A-Level Secondary School, Olenjolaim in square bracket. Make sure you subscribe. You share this material with your friends, with your schoolmates, with your classmates, with your young brothers, with your elder brothers. You see, it's the time for the digital technology to impact the life of the Tanzanians, and even the life of A-level students. So join me in the next lecture. May God bless you, and stay tuned.